Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing carbonyl metallates over the last few lectures and looked at the synthesis, reactivity and properties of this special kind of transition metal carbonyl complexes, how they were synthesized, what are the reactivity, so on and so forth. And today we are going to take up an also very important application of transition metal carbonyl metallates, particularly of that of Coleman's reagent. Now, this is a very useful chemistry which is practiced day in and day out in the world of synthetic organic chemistry, and this is based on iron based organometallic compound called Coleman reagent. And the formulation of this compound Coleman reagent is Na2 FeCO4. So, it is a carbonyl metallate iron metallate complex and used in functionalization of organic halogen compound. Organic halogen compound. So, here we see a very important application of these iron carbonyl metallate, which is called Coleman reagent in day to day organic synthesis. I must note that this application is more on stoichiometric fashion in the sense that Coleman reagent is not a catalyst, it is just a reagent for performing this functionalization of organic halogen compounds, and hence its reactivity is done in stoichiometric fashion. But nonetheless, this is a very important reagent as it allows a wide variety of functionalization of organic compounds, and we are going to look at these in details right now in this particular lecture. Now, the interest in iron chemistry is all the more important because iron being naturally abundant, there is a significant interest in utility of iron not only in reagent purpose as we seen in this Coleman reagent, but also for its ability to catalyze chemical transformation. So, this iron is a contemporary topic of interest where significant amount of efforts are being directed towards utilizing the chemistry of iron for various catalytic as well as stoichiometric transformations. So, with that brief introduction about Coleman's reagent, let us take a look at some of the reactivity that Coleman reagent performs. Okay. For example, Na2 FeCO4, which is the Coleman reagents, when treated with Rx provides this anion now. In this is the iron anion with a iron organometallic species formed, which when treated with D plus gives Rd. Similarly, when Coleman's reagent is treated with acid chloride, then one forms this iron acyl complex this is also a metallate anion, and when the same is treated with H plus gives aldehyde. Now, if this iron alkyl metallate when treated with carbon monoxide, then migratory insertion of CO happens in the metal alkyl group, which is a very common property of transition metal alkyl complexes, giving this transition metal acyl metallate. So, this is a direct conversion of iron alkyl to iron acyl complex. Similarly, if this alkyl is treated with R dash X, then one gets this ketone where there is a CO inserted, one gets this R C O R dash, where one CO has migratory inserted and then R dash X gets in ketone, and the same can be obtained from this acyl complex by treating with R dash X. So, here what we see is a nice demonstration of arriving at the same compound by two different routes. One is by the right hand side, the other is by left hand route, and in one it goes via the formation of the iron alkyl complex, for the other it goes via the formation of the iron acyl complex. Now, the iron alkyl complex similarly when treated with oxygen gives acid and the acyl complex also when treated with molecular oxygen produces this acid. Similarly, when this alkyl complex is treated with halogen X2, then one gets the acid halide and similarly the acyl complex when treated with X2 also give the acid halide, and acid halide when treated with an amine produces amide, acid halide when treated with an alcohol produces ester and acid halide. When treated with water produces acid. So, the utility of Coleman reagent is nicely demonstrated, that when treated with organic halogen compounds and followed by workup, one can obtain aldehyde, one can obtain alkane, one can obtain ketone, one can obtain acid, one can obtain acid halide, one can obtain ester, and one can obtain amide. So, what one sees that depending on the treatment, so many different, for example, alkane, aldehyde, ketone, acid, acid halide, ester, amide. About 7 different organic compounds can be obtained from organic halogen compounds using Coleman reagent. So, Coleman reagent is a nice demonstration of utility of iron organometallic compound in day to day organic synthesis. The advantage of Coleman reagent is high yield and high selectivity. Is high yield and high selectivity as organoids do not, as organoiron anions do not add to carbonyl or nitrile groups. So, for example, no protection required. For example, reaction of this acid chloride with Na2 FeCO4 in THF and the molecular and pressure of CO and acetic acid gives high yield of this aldehyde, 98% yield. Similarly, the reaction of this bromonitrile reagent with Na2 FeCO4 THF CO and when treated with acid chloride C7 F15 Cl produces this ketone nitrile in 72% yield. So, here too what we see is this high yields and selectivity which are the advantages of using Coleman's reagent. So, limitations of Coleman's reagent is that FeCO4 2 minus acts as a strong base in case of tertiary halogen compounds and can affect HX elimination. So, the end of discussing this Coleman's reagent, which is the iron tetracarbonyl dianionic compound and its utility for functionalization of various organic halogen compounds. And what we have seen that the advantages of Coleman reagent arises from its high yield and selectivity for these transformations. It can lead to wide variety of functionalized organic compounds, for example, from acid, ester, alkane, amide, ketone, aldehyde, so on and so forth. And that speaks volumes of about how the utility of iron based organometallic compound came into day to day use of organic synthesis. So, with this we are going to start another interesting class of organometallic compounds. These are carbonyl metal halides. And are known for most of the transition metals. These transition metal carbonyl halides are prepared directly from metal carbonyls and halogen. And the reaction is given as FeCO5 plus I2 giving FeCO4 I2 plus CO. So, here we see a reaction of iron carbonyl with iodine giving the iron metal halide and CO, and iron has been oxidized from its 0 oxidation state over here 2 plus 2 over here by this oxidative addition of iodine. Now, we are going to take a look at few other examples of these carbonyl metal halides, and these two also involves preparations from metal carbonyl with iodine. For example, Mn2 similar to the iron carbonyl, this one is Mn2CO5 plus iodine gives 2 Mn CO5I, which when heated at 120 degrees centigrade loses 2 carbon monoxide molecules to give CO Mn CO 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 Mn iodine CO 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 CO. So, here what we see is that iodine has oxidized this dimeric manganese carbonyl compound, and each of the manganese center got oxidized by 1 unit. So, they have got turned to manganese 1 compounds, and when heated they dimerize with elimination of CO, where we have a dimeric Mn2 CO8 compounds with I2 2 bridging iodide. Now, in presence of pyridine, the dimeric bridges of iodine is broken to give the monomeric complex Mn CO 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 PY iodine. So, here this iodine bridge is broken and is replaced by pyridine. Now, in excess pyridine, another of the CO is lost to give the following Mn CO iodine PY CO complex. So, here we saw the second method or second example of methods for preparing carbonyl metal halides, and these two involve reaction of metal carbonyls with iodine. Another method is preparation from metal halides and carbonyl, that will also give metal carbonyl metal halides. Prepared from metal halides and carbonyl. For example, PtCl2 plus 2CO giving this chloro bridge platinum dimeric complex and these platinum compounds containing 2 chloro bridge and 2 carbonyl and 2 terminal chloride atoms. It must be noted that for several late transition metals like palladium, platinum, copper and gold, no stable binary no stable binary neutral carbonyl complexes are known. They form ternary carbonyl metal halide complexes. So, with that, let me summarize the points that has been discussed in today's lecture. We have looked into a particular reagent, which is the utility application of transition metal carbonyl metallates, and this is this Coleman reagent, which is Na2FeCO4, and this Coleman's reagent is extensively used for transforming organic halogen compounds to functionalized compounds. So, this is an extremely good reagent for functionalization. We have looked into the flow diagrams and we have seen about 7 or 8 different compounds, starting from alkane, aldehyde, ketone, amide, ester, acid can be formed using Coleman's reagent. One important attribute of Coleman reagent is that it provides functionalized products in high yields and high selectivity. So, that is kind of the advantage for using Coleman's reagent. What we had, I would like to stress that Coleman's reagent is a beautiful application of iron organometallic compound as a stoichiometric reagent, and in addition to that, the utility of iron organometallic compounds in various organic transformation, but as a catalyst or in a catalytic fashion is also of significant contemporary interest, and currently a lot of work is being done in this area. Also with that, we have concluded our discussion on Coleman's reagent and moved on to carbonyl metal halide compounds. We have looked at various preparative methods available for preparing these carbonyl metal halide compounds, and basically the two approaches had been react metal carbonyls with halogens to give the carbonyl metal halides. We have seen two examples, one of iron and another manganese for that, and the other approach is about taking metal halides and reacting that with carbonyl, this involving platinum. In this regard, it is worth noting that for very late transition metals like palladium, platinum, copper, gold, no such binary neutral carbonyl complexes are known, but for these elements ternary carbonyl metal halide compounds are known. So, with that, I would like to conclude today's lecture, and I would take up these transition metal carbonyl halides and their properties in bit more details in the subsequent lecture which would follow next. So, I thank you for being with me in this lecture, and I look forward to the next lecture on transition metal carbonyl halides, which will be studied in more details in the next lecture. Thank you.